You want to learn how to push your tools harder, run faster feeds, and still extend tool life? Today, I'm going to walk you through how chip thinning and high feed machining actually work, and why understanding the math behind them can completely change how efficient your shop runs. I was a machinist for decades, and now as CEO of PT Solutions, I want to see these principles applied across the industry so shops can run as efficiently as possible and we can continue to grow this great industry of ours. Let's break it down so I can take this knowledge back to your machines. First, let's talk about what makes high feed tools unique. These tools are designed to take light depths of cut at extremely high feed rates. What makes this possible is axial chip thinning. But here's the interesting part. They still remove a surprising amount of material, and the biggest benefit is consistent, predictable tool life. That's exactly why they were developed, to give machinists more efficiency without stressing the spindle. Now, before we get too deep into high feed tooling, let's look at where this concept comes from by comparing a 90-degree cutter to a lead angle cutter. With a square shoulder mill, the feed per tooth is equal to the chip thickness. With a 45-degree lead angle mill, the chip thickness is less than the feed per tooth by about 30%. And the smaller the lead angle, the thinner the chip. On top of this, the lead angle also directs the cutting forces up towards the spindle rather than the side of the tool, which makes them ideal for long reach applications. Most high feed mills on the market have a lead angle between 10 and 25 degrees. This gives a chip thinning factor of 2.5 to almost 6 times the optimum chip thickness. Tool manufacturers take this into account based on the specifics of their design. Typically, they include this in the factors in their catalogs. They also give a maximum depth of cut. Do not exceed that depth of cut. If you exceed that depth of cut, the chip thinning no longer applies and you will destroy a tool. Now that you understand how and why they work, let's talk about how to select the best tool for your applications. There's a lot of really good high feed mills on the market from the biggest brands in the business, and they all have strengths and weaknesses. There are a number of factors you should consider when selecting a high feed. What materials are you typically cutting? High feed mills show the greatest value in ferrous and difficult to machine materials. If you're cutting mostly steel and iron, a tool with a relatively neutral geometry and a decent edge prep will work the best. If you're cutting mostly stainless or high temp alloys, a more positive geometry with a sharper cutting edge will typically perform better. What's your machine capabilities? This is one of the biggest factors. If your machine is capable of very high feed rates and maintaining those feed rates with complex tool paths, then tools with higher flute count will allow you to maximize your machine's capability. What kind of part geometries and how many parts do you need to make? High feed mills are ideal for parts with complex geometries, including tapered surfaces, pockets, large holes, and long reach applications. Job shop or low quantity parts are also good for high feed milling because they can be used on a large variety of applications, typically not for high volume parts. Another important consideration is tool diameter. With most cutting tools, the part geometries tend to dictate the tool diameter you should use. But with high feeds, it's a combination of part geometry, machine, and reach. For example, on a Cat 40 machine like the one behind me, I would not suggest a high feed larger than 2 inch. Better to travel a little further at a really high feed rate and optimum parameters than to take a wider cut. Even with light depth of cut, the surface engagement on a high feed is more than it is on a square shoulder mill. Now here's why this matters. Programming software will often give you default parameters, but those defaults don't always reflect the true cutting diameter, especially with ball nose or high feed tools. If you understand the math, you can confidently push your feed rates without burning through tools. And as always, the golden rule is this: know your maximum depth of cut. That's where efficiency and tool safety meet. In the solid carbide world, these results are even more impressive. Add more flutes to smaller high feed tools, and suddenly you're hitting feed rates that would have been unthinkable in the past. This is exactly where the industry needs to focus. Smarter programming, more aggressive cutting, and better tool life. So the next time you're programming a part, don't just plug in the standard numbers. Take a minute to do the math, apply the chip thinning, and you'll see faster cycle times, longer tool life, and lower overall cost and greater profitability. If you've got a specific application you'd like us to cover, drop it in the comments below. Or if you have a method that's been working great for you, I'd love to hear about it. Don't forget to subscribe, because in the next videos, we're going to show you more ways to reduce your cycle times, increase your profits, and your efficiencies.